Very good morning, everyone. So I hope now you are much more comfortable with the programming of graph algorithms like prims, etc. Basic data structures are clear and you have started practicing. Take time. If you have any doubts, we'll discuss. If needed, I'll show the sample answer code also later. The only thing in the last class I told was for the answer set, you have to plan what data structures you need. So suitable data structures you can choose. How will you store your answers? So maybe you can keep on storing your vertices, which are being selected. In some way, you keep on storing vertices. And through vertices, effectively, you can have the answer set ready. These vertices also know their parent. So through that parent, you can also come to know which edges are selected and edges considered are also coming. And then accordingly, you can regenerate your MST or the total graph. So anything you can choose or any other alternate as you like. So for an answer set, you have the freedom, the way you want to show. If you want to show it as a MST drawns in some way, then accordingly you can have. So then maybe one alternate, you can then second alternate can be store sequence of edges selected, edges and their sequence you can store, and through that also you can result or show your result. So you have the choice, anything you can do. And there can be many more like that. So, but let's go further. Till now, what we were using was MST, etc. But in real life, Google Map is one of the fantastic example which we have seen. And Google Maps don't just talk of MST, etc. Effectively, they talk of the shortest paths effectively. Yes, path or route from one city to other. Shortest could be in terms of a time or in terms of a distance or in terms of anything else. Nowadays, by default, you get time. For our standard discussions, we are more focused on distance, but it doesn't matter. That will be how your edges are stored. But before that, you know that you have a concept of a route or paths. So let's go one by one and find out what do we mean by path versus this. So first thing is, till now edge I know, path we will define formally, and then we will come to shortest paths. So path or route, whatever you use word, Google Map, you can say route, but ultimately in graph, path word is used. So path effectively will mean that you are traveling from one city to other. For example, I am traveling from KKR and I have to go to, let's say, Chennai. So Chennai, I could go, say, via Delhi, or maybe via Delhi to then Delhi, then maybe from here Rohtak, not Delhi, then from Rohtak to, let's say, Jaipur, then Jaipur to, let's say, Bombay, and then Bombay to Chennai. Delhi, Chennai could be another route. Similarly, there could be from here to Delhi, say Delhi is already there. From Delhi, you could go to Nagpur, Nagpur to some other route and like. So effectively, I have multiple paths possible, multiple routes possible. So you can easily say that if I have to go to Delhi also, there could be a route like going Kurukshetra to Rohtak, Rohtak to Delhi, Kurukshetra to similarly some other city and then to Delhi, or there could be a direct route Kurukshetra to Karnal, Panipat, Sonipat. This is a direct route. So when I say edge, there is a direct route available. I know that. Path, effectively, it means, say, if I have to travel from U to V, from vertex U to V, then path means one or more edges in sequence to be traversed. In sequence, of course, so that sequence is important, to be traversed to reach from U to vertex V. From U to vertex V. So one or more edges. For example, if I have a graph, let's say 1, 2, 3, 4, let's say 5, say 6, and I have many connections possible like this, and maybe many connections like this, and many more. Say there are certain weights 3, 5, 2, this could be, let's say 10, this could be, let's say 7, this could be 4, this could be 3, this could be 8, like this. So I say path from 1 to 4. Normally we show 1. I'll have this as a symbol known as reachability symbol. So it means effectively reachable. Obviously 4 is reachable from 1 in a directed graph. So direction arrow is being considered. We are talking of directed edges. So effectively it means there are multiple routes possible. Say path 1 means directly go 1, 4. Then path 2 could be, let's say 1, 6, 4. Effectively meaning edge 1, 6 followed by edge 6, 4. This means direct edge 1, 4. Similarly, there could be path 3. Path 3 means I have, let's say 1, 2, 3, 4. Effectively meaning I have edges 1, 2, 2, 3, 3, 4. So multiple paths are possible. Of course, all paths are considered by Google Map, and then Google Map finds the shortest. So for knowing shortest, we define weight of the path. For example, I say path 1, 4. So weight is obviously 10. What about path 6, 4? Path 6, 4 effectively mean how much distance I will travel. So I'll travel 7 plus 4, that is 11. So similarly for other path, I will travel 3 plus 5 plus 2 to reach 4. So effectively weight means nothing but it is a summation of all weights of all edges of that. So I'll say summation of weights of all edges in the path. It is obvious. That will be the total distance traveled, and obviously that will be called as weight of the path. So for example, path 1, I can easily say the distance weight is 10. Path 2, the weight is 164. That will mean 7 plus 4. That means 11. Path 3, 1, 2, 3, 4. That means 3 plus 5 plus 2. Let's say 10. So this plus this plus this. So I have 3 paths with the 3 different weights. So obviously this can be shortest or this can be shortest. Both are equal. So then obviously I define something known as the shortest paths. The shortest path obviously means out of all possible paths or out of all existing paths, we have to find the shortest. So I'll say out of all existing paths, the path with least weight is the shortest, with the least minimum weight. This is what I want to find out. So obviously, shortest path has a lot of applications, and Google Map definitely using this. So shortest path algos, they are effectively 2 categories. One is called as a single source shortest path, and obviously other is called as all pair shortest paths. As the word suggests, single source will mean that the source will be predefined. So source will be fixed. For example, if I say source is 3, then I want to find out paths for all 3 to 1, 3 to 2, 3 to 4, and let's say 3 to 5. So I want to find all paths and shortest paths from 3 to all vertices. This is what is called as a single source shortest path algorithm. So going further, let me just say, I want to go with single source shortest paths. So for single source shortest paths, we will be proceeding one by one, and we will say there are many algorithms available. To start with, we will use a Dijkastra's algorithm. Dijkastra. It is named as a Dijkastra, and J is silent in speaking. So it is called as a Dijkastra's algorithm. And in this algo, one of the simplest and very highly useful algo, it will work for obviously for directed graph. So we will be all talking of all single source shortest paths for directed graphs. Of course, the concept can be similarly used for undirected also. But with directed, definitely it will make more useful because reverse direction might not exist. And we would like to ensure that we are not going to have that also possible. But yes, you can definitely apply to undirected in a similar manner. So with the Dijkastra algorithm, assumption is nothing new. You already know that all weights are non-negative always. Weights of the edges. That means all edges weights is greater than equal to 0. Of course, we have not used till now negative weight, so we file this is perfectly fine. Distance can never be negative, that is also perfectly fine. But mathematically, in graphs, negative weights can exist. Mathematically, these will exist. Negative weights are allowed, and they can impact the algorithm. And we are going to use these also, or make algos these for these also. So next algos will use this. For the time being, nothing new, but this is what we assume. So knowing this, let's take a graph over which we will be doing this and understand the working. So let's assume this is a sample graph. I'm using the same graph which is in the book given. And let's assume that the source is a 3. Intentionally, I'm starting with non-1. So I can start with 1. So I have numbered them that my source vertex is a 3. So first thing, I say that initially I will say distances for all vertices are 0 or are 0. Distances for all vertices will be taken as infinity. So I'll say distance for all vertex will be initially taken as infinity, as initially nothing is defined, and slowly we will keep on improving. So from source, let's say 3, I will say distance of the source. So I will store here distance. So distance for the source will be obviously 0. This will be 0 now. Okay. For others, distance is plus infinity for the time being. I'm storing plus infinity everywhere. For every vertex, the distance is being stored. Initially, it is plus infinity. I start and make distance as 0, step 1. Then I say, so initially what I have taken is my answer, and I have selected source vertex and distance being 0. Now I say, out of 3 only I have to proceed. So I will say select and see its all outgoing edges. Once you look at the outgoing edges, I am going to have selection of some edge which will be guaranteedly best. How? I say either I could go this side or I could go this side. These are the 2 possibilities. Then I say, because a 5 is minimum out of these 2, I say this edge is guaranteedly going to be used, and 2 is guaranteedly final, and 2 can be reached with the distance 5. So I say 2's distance will be 5 as a shortest, and is a shortest. Guaranteed, for sure. Why I claim this? The logic is simple, that from 3, either I can reach to vertex 2 with direct edge, that is 5, or maybe indirect edge, indirect path. That will mean from 3, I will go to, let's say, 4, and then from I will go, let's say, to 3, or similar like that. But That will mean from vertex 3, I have to go to some other vertex whose distance will be guaranteedly greater or equal to 5. So if I go indirect, if 3, 2 is not used, then I have to use a 3 to some vertex, and then from some vertex via someone ultimately to 2. But going 3 to some vertex, this is going to be guaranteedly greater than 5 weight. So whenever I will reach to 2, this root will be greater than equal to 5 plus next weight. Could be 0 also, but minimum this is guaranteedly 5 or higher than 5. So I say 2 is guaranteedly selected as correct, and I can claim that 2 can come into my answer set where its distance is guaranteedly 5. So this will be my next step. Then I will say once of 2 is selected, now I have the similar logic to be applied via 2. So I will see, can I reach to other vertices via 2? If yes, can that distance be lesser than the previous possibility? If yes, improve the distance. Otherwise, I will not go via 2. For example, 2's outgoing edges now to be considered. So 2's outgoing edges are these and this. So I have 3 2 outgoing edges. One is this, and other is this. So I say from 2, I can go to these vertices, which is vertex 1. Vertex 1 initially has infinity distance. If I go via 2, the distance will be 5 plus 2, so 7. Earlier one is plus infinity. Now I can say this will be 2's distance because I'm coming via 2 plus this weight, that is 2. That means effectively 5 plus 2 equal to 7. This 2 is this weight. Similarly, 5. 5 is earlier infinity. Now I say, if I can come via 2, yes. So it will mean a 2's distance plus weight 9. That means 5 plus 9 equal to 14. So this becomes this distance. Similarly, this weight of the 4 was 10 earlier. This was earlier 10 because via 3 it was reachable. So distance I updated for this also. Distance for 2 was also updated. This was a 5. So 5 was guaranteedly correct and selected. 10 is one possibility. Now I am going to see via 2 can I reach? If I come via 2, it will mean 5 plus 3, that is 8. So 5 plus 3, 8 is better. So I will say, let's improve this distance and consider it as 5 plus 3, better than 10. So this is better than 10. I will go for this. Better than 10. And that's why this is via 2. So this distance also updated. So this becomes 8. This distance is 14. This distance is 7. Now I say, because 1 is at the least distance, this is going to be again the best selection, and this choice can be the best for proceeding further, and once the shortest distance is found. The way we said for 2 it was final. Now if I come to 1 via some other one, they will take more than 7 in total to reach to that vertex, and additional also will come. So I say 2's distance is final. Once the distance is final, I will say let this one be in the answer set, and once the distance is known to me, that is a 7, and then same process to be repeated. From 1 I can go to 5 via this. From 1 I can go to 3, but 3 is already selected, not to be done, so nothing to be bothered. Then to 5 I can go via this. So I will say 5 I can reach via 1. That will mean 7 plus 6. So this will become 7 plus 6 equal to 13. I can easily see this 13 is via vertex 1. So earlier I have a distance of 14. Now I can get 13. So this also to be updated. So this will be removed. This will be made 13. 1 is already selected. So accordingly, we will keep on proceeding. And via this, all that will be finalized. Similarly, this distance at present is 8. If it can further reduce or not, it will be seen. And accordingly, one by one, we will keep on selecting. So this is how Dijkastra algorithm works. So Dijkastra's algorithm working like this will mean now I can make the logic. So effectively, one liner for Dijkastra's algo can be written. Main logic is one line only, and that line, if you remember, will make the things easier. So what I should say, I will say this will repeatedly select, or I will say repeatedly select the corresponding lightweight or lightest vertex. Lightest obviously will mean the shortest distance. So I'll say lightest vertex V, repeatedly select lightest vertex, let's name it as U because it will become source vertex after some time, from uncovered vertices or uncovered set, and add it to answer set, add U to answer set, and then what to do? Based on or outgoing edges of U to be considered for improving the distance, of corresponding remaining vertices. Effectively, this explains the overall logic of this. Now, effectively, one I say is this logic. So I say once I had selected some vertex U, I am going to consider its outgoing edge. So some outgoing edge will be considered. So if I am talking of edge UV, this might improve the distance of V or might not improve. U is final. So this is already selected vertex now, just selected. In this iteration, this is the U, and V is going to be the adjacent vertex of V, one by one. So this is adjacent vertex. So V's distance may improve, V's distance may not improve, may improve via this, via UV. So that is what. So this step I say is going to be called as relax. So I will say relax the distance based on UV edge. As we could say, like earlier I said that the vertex 5, for example, above, when I said vertex 5's distance, so like I said, once 2 was selected, so I said 5's distance earlier was at present, initially or presently infinity, and via 2, that is via edge 2, 5, it will become the 2's distance plus weight of edge 2, 5. Just to see back, I said 4, 5, once y came via 2, 5 plus 9, earlier that was infinity. So I said this was 5 plus 9, that will become 14. Earlier that was infinity. Later, 1 selected, and then based on 1, I said that 1, 5 edge relaxation will be tried. Relaxation of 1, 5 will mean effectively 1's distance plus weight of 1, 5. This will be considered for 5's distance to be relaxed or not. So earlier 5's distance is 14. This will become 1's distance we have used as 1's distance was 7. And then I could say this was 7 plus edge 1 weight 1, 5. That was 6. This 30. So relaxation could be done over this like this. So this step I say as relax. So now knowing all this logic, my programming is simple. Programming, or effectively now I will not write the full code. I will write the pseudo code or main logic. The reason is simple, that I don't want to give you spoon feeding of the code, and further whatever code I give could be applicable for adjacency list. Now the pseudo code will be applicable for any representation, and like adjacency list representation or adjacency matrix representation, and you could simply implement accordingly. So if I say void Dijkastra, let me again use the normal pen so that we remember that the color is by default the red we are using. So I'll just continue with that. I'll just remove and rewrite this. So I say I have a void and Dijkastra algorithm. Of course, whatever parameter you need, you also need to know the source. So effectively, now if you call whatever we did with the prims algo, same logic can be still applicable, because still I require the vertex lightest. Lightest vertex effectively mean the min priority queue can be used. So min PQ will be still useful, and the same logic to find out can be useful. So effectively, my vertex node will remain, I'll say all things remaining similar. I'll say first of all, edge node, no change needed. Edge node is perfectly same as we used in prims algo. Vertex node can be again similar, because vertex node also we require the same thing again. The only change I will make, use word predecessor instead of a parent. Because here I have firstly not a tree, parent child word is used normally in tree, and parent is no more now applicable in graph. Secondly, I have a sequence of edges. Each of them will have some previous predecessor. So it's a cumulative or successive use of edges, one after the other. So previous predecessor will be used. So effectively, vertex node will remain more or less same. I will have the predecessor stored. I will have the corresponding in PQ flag stored. I can have the PQ index stored, and I can have the pointer. So all that remaining similar, and I can have array of vertices without much difficulty. Similarly, PQ, which we earlier used, PQ node also again same usable. The only change we will do is that in this earlier we had vertex. Now we will use word. So we will use word distance instead of saying key. Because ultimately we should have meaningful variable naming. So instead of word key, I will use the word distance. That is it. So effectively my PQ node means I have same thing again, vertex and distance. And then array of this can be used. So PQ will be my array, and again 51 or whatever. So everything remaining same. Vertex node also, graph also. So this is my overall graph with the array of vertices. And I can have all that in the similar manner if adjacency list representation used. For adjacency matrix, you can accordingly change. But more or less my logic remaining similar. So let's start writing the code without much difficulty. And I will say, of course, Dijkastra's algo. Source needs to be informed to me. Rest everything, whatever you require. So step one, effectively, you have to do initialization the way you did earlier. Initialization effectively will mean for all vertices, you have to effectively initialize a predecessor, let's say as -1. You have to initialize, say, in PQ flag. Maybe initially they are in priority queue. You will have it 1. Then your PQ index, you can have accordingly used initially, whatever you initialized, you know that. Then similarly for your PQ also you initialized your vertex number. say this also you make equal to I. Then your key, which is now called as a distance. So this you will initialize with the plus infinity. So all this initialization will be completed. Why I am needing in PQ, why I am needing a PQ index? Just look at this one line. I said, select U from uncovered vertices. So if uncovered means in PQ, if that vertex is in PQ, I need to do that. And outgoing edges of this to be considered for improving the distance. Distance is stored in PQ. So I need a PQ index also. So accordingly, PQ index needed, and a distance to be updated. Improve will still mean a decrease key, kind of a thing. So everything remaining similar. And this all outgoing edges, so effectively will mean adjacency list to be traversed. So now you recall, effectively the logic is more or less similar to Prim's algo. Let's write the code, it will be more clear. Obviously, now I can say, now source is defined. So I should say source distance to be made as 0. Earlier, everybody is infinity. Source predecessor will guaranteedly remain -1. And predecessor will store the vertex number through which this vertex will be reached. Effectively the same which we have done earlier. So what I need to do? Now after this, my all vertices are in PQ. So effectively, I have to build heap first so that source reaches on the top. So I have to do build min heap, and accordingly that PQ will be converted to the heap file so that my source reaches on the top initially, and later the selected vertex will be always used. The lightest weight or lightest vertex will be on the top. Every time I will have the lightest vertex, distance with minimum. So I will say lightest vertex will come on the top. So every time this will be done. Initially, source will reach because the source has a distance 0, all others have infinity. So this will reach to the top or root, and others later. So obviously then my logic is again simple. I can say while PQ is not empty, I have to repeat. I have already said that successively go. Initially, my answer set is empty. So if you want to assign answer set in some way, use it, choose data structure, and accordingly add to this source. Or maybe source also we will add via extraction. When extract min will be done, that time we will add. So choose your data structure, initialize whatever you want to do. So obviously first time I have to do is extract min, and that I call as U. So vertex U is selected, and accordingly whatever flags in PQ etc. you have to check etc. and U to be added to answer set. Whatever way you want to store your answer set, add it to there. So whatever, all those you have to do, you will do obviously. But what is more important now, based on U, effectively, you have to do the corresponding outgoing edges of U to be considered. So I have to effectively consider for each vertex V, which is belonging to adjacency list of U. Now, if it is adjacency list based, temp not equal to null, etc., you will use. If it is adjacency metric based, the corresponding row you will traverse and find out. And I will say, effectively, what I have to do is relax distance of V using edge UV. But when to relax? Based on some if condition. So I'll say, I'll just remove this. I will have to do, because if this is to be done or not, I have to see, and then I have to relax. So I'll say, if something, what if this V is in PQ, only then if V belongs to PQ, because if V is already in answer set, nothing to be done. So if V belongs to PQ, one condition, and if the distance of V is earlier greater. So V's distance is earlier known to me. If V's distance is greater than the possible new distance, what is the new distance? New distance is going to be U's distance. U's distance is a source to U with the shortest distance, which is final, plus weight of edge UV. Via U I am reaching, so V's distance will be now modified to become U's distance, which is already minimum, and via UV edge U will reach. So this weight is currently in the adjacent edge nodes. We have already done like earlier. So, but in adjacency matrix, we can take it from the corresponding somewhere else. If this is there, effectively, I have to relax. So this condition you can put in the relax also, or you can relax V's distance based on edge UV. And what is the relaxation? Relaxation is simple. Relaxation is equivalent to saying that V's distance will be updated. V's distance will be equal to U's distance plus weight of UV. Effectively, this is going to be a kind of a decrease key because the weight is decreasing. So V's distance will be improved like this. And whenever distance improved, this also means that the predecessors have to be very predefined. So predecessor changes. Earlier, V's predecessor was based on the previous distance. Now V's predecessor will be U. So effectively, relaxation means this. And having said that, my work is already over. So this is effectively nothing but first, V is a distance equal to the new value. And second, V is a predecessor to be changed to be equal to U. So that's it. More or less work is done. And this is what is going to be the overall logic for this. Effectively, if you see, it is almost similar or almost same as the Prim's algo. The only thing is in Prim's algo, plus etc. was not done. Rest everything is same. So the time complexity will also remain same if you talk of adjacency list-based representation. So adjacency list-based and min-heap-based or binary min-heap-based, the complexity will still remain same, which was order of V plus E log V. Of course, in Prim's, we said E is greater than equal to V, but in this case, no guarantee. If E is guaranteed or if E is greater than equal to V, then we will say it is order of E log V. But because the graph is not guaranteed to be directed here, or guaranteed to be connected, so we cannot claim always. But if I want the vertices to be reachable from source, the graph should be connected at least from source. So obviously, normally this will be true. But this is the. So it is similar. Aim to implement using syntax, implement for both for adjacency list as well as for adjacency matrix also. So if you try both, adjacency matrix based implementation will help in pseudocode. Complexity will be different. Of course, time complexity will be different. May not be E log V that you have to calculate because adjacency matrix is traversed in a different manner. So that can be possible. But you must implement of your own these two algos. Then quickly going to another that we have said negative weights were not allowed. Why? You can now easily see that I said from vertex 3, I went to vertex 2 and said 5 is final. Because this side I could go with 10 weight. And I said it will be more than 10 guaranteed every time after this. But if from vertex 4, let's say this weight was -8 I will be reaching to 2. So my 3, 4, 2 will mean 10 minus 8, that is 2. So 5 will be not final. So hence my will be not final if negative weights were allowed. So my Dijkastra algorithm doesn't work because that is assumption that this was final and it was an optimal choice, but now this is no more true. So if negative weights exist, then we have another algorithm which is known as DAG, shortest path. So negative paths, negative weights will be allowed, where DAG word stands for directed acyclic graph. So directed graph we are already using, but now we are going to use acyclic graphs. And negative weights allowed. But negative weights allowed, acyclic means cycles not allowed. Cycles not exist. Not allowed. So now cycles won't exist. Earlier we had cycles also. In Dijkastra we had cycle also. In Dijkastra it was allowed. We had no problem, but negative weights were not. So in Dijkastra cycles were permitted, but negative weights were not. In DAG, negative weights permitted, but cycles not. Later we will have another algo where both will be permitted. But now in case of a DAG, acyclic graph logic, so that is acyclic. So in this case, the shortest path, I cannot claim vertex to be the slightest vertex to be final. So lightest vertex, which I am claiming now to be finalized, not final now. Because later it can get further reduced. So effectively what I need is now, whatever vertices can relax others, in that order I should consider. For example, if I have, let's say, vertex 3, and I have vertex 2, then I have like this, but I have vertex 4 also, somewhere like this. 4 can also relax like this. So I have to consider 4 also. I have to consider only then 2 can be finalized. Because the 2 is reachable via 4 also. So this was one distance. This is a 10. This is minus 8. So I have to reach to 2 in a way that after reaching to 2, once the distance will be final only when further no other vertex makes a reachability to 2. Means I should order my vertices in a particular way such that reachability is in a particular order. Reachability or direction of the edges is on order. That will help me not to go from 3 to 2 and in a particular order. And this we have already done. This we have done already. And if you recall, we have used effectively topological sorting. So topological sorting, we have exactly achieved the same. So in this case, if I say from 3, I will not go to 2 until unless anybody who can bring me to 2 are covered. Once I go beyond 2, via 2 only, others will be reachable. And from others, 2 or previous are not reachable. That means 2's distance will be final now, because no other vertex is left which can bring me towards the 5. And effectively, this means my topological sorting order of vertices can be directly used to finalize distance of this. Remembering this, effectively, I can say whatever graph I had, if it is acyclic, so topological sorting is possible. And topological sorting, let's say I have some vertex, let's say 5, then I have vertex 3, then I have, let's say, some vertex 2, then I have some vertex, let's say 4, then I have some vertex 5, 1. So there could be a lot of connections like this, like this, like this, like this, like this, like this. But it is guaranteed that if from 5 I am reaching here, let's say this weight is 2, this is -5, this is 6, this is 4, this is -2, this is 7, this is -1, this is 6, this is 5, anything like that. But I say, so I will start from this order. Maybe my source is this. So I say, I will start from 5. From 5, 2 is reachable, or I can start from 3. But once I go in this order, via 5, any relaxation will be finalized. Via 5, relaxation will be final. Relaxation can be done first, although we will not need that, because if a source is 3, 5 is not reachable at all from 3. We have already seen. So 5 is not reachable, means 5's distance will be guaranteedly infinity. So via infinity, no relaxation will happen. Hence, 5 has no meaning. So whether I consider 5 or not, absolutely no issue. Then I will come to 3. Via 3, all relaxation will be done. And then I will reach to 2. Now, once I have reached to 2, or if 2 was not, let's say this was, let's assume 4, and this was a 2, so that you don't get confused with earlier. So if I am able to reach 4, once I go beyond 4, nobody can relax for the vertex 4, because no incoming edge to 4 will happen after this. So that is the logic. So based on that, I can easily see no PQ needed. Absolutely no PQ needed, because I'm not doing any kind of a min heap or minimum distance to be finalized. Vertex order is needed. So vertex order I can use in a particular way using topological sorting. PS order needed, but PQ not needed. So my edge node will remain same without any difficulty. Vertex node now can be simplified. In vertex node, I can have the first predecessor, which is similar to parent. So predecessor will be stored guaranteedly. In PQ, I don't need now, because PQ is not maintained. PQ index, I don't need now, because not maintained. And of course, I need adjacency list pointer. So that I need. So this will definitely go. So what else I need? In PQ, earlier I had the distance stored. Now PQ I am not maintaining. So distance also needs to be stored. Distance is a belonging to a vertex. Yeah, this is relevant for each vertex. Hence, now this distance should be stored with a particular vertex. So effectively now my vertex node will be modified. So my vertex node will have effectively nothing but I will have the predecessor, the distance, and the adjacency list pointer. And then here I have edges, weight, and connections like this. So this will be now my graph. This will be my edges, and no PQ needed. So this way I can easily work on this. Now, having said that, my logic or my application for this DAG shortest path, this logic is simple. Of course, first of all, I need to do the topological sorting. So do the topological sorting, and order or list is maintained. Once done, initialization to be done after this. So initialization effectively will be simple, means effectively your predecessor to be initialized with -1, distance to be initialized with infinity. For source, distance to be improved. So source distance to be made 0. Obviously, that is simple. And now onwards, I will travel. So effectively topological sorting order I have to do. So I will say travel, or for each vertex U, it will become the source vertex ultimately. In topological sorting order, I have to do. What I have to do? U has a certain outgoing edges. So effectively, I have to relax the distance, or I'll say for each vertex U, its adjacency list to be traversed. So I'll say for each vertex V belonging to the adjacency list of U, all outgoing edges of U to be considered, and based on that, effectively relax. Of course, in relax, you can have a condition. So you can say if distance of V is to be greater than the old distance and compared to via U, distance via U, I will say. So you know how to write that logic. I'm not rewriting. So distance via U, if that is earlier distance is greater, so you will be relaxing that. And based on that, effectively, you will be covering one by one. So effectively, in TS order, whatever vertex covered, that distance becomes final. Because no incoming edge further can reduce that distance, and that distance becomes final. So here the logic becomes in this order. Having said that, now I can quickly see that this will also work. In the book, one example is given. You can check and work on that. If there are doubts, it will be discussed, but I think it will be easy for you. Time complexity. Topological sorting, time complexity, I always know it is theta of V plus E. Initialization, obviously theta of V. This is theta of 1. This for loop, how many times it will execute? TS order means V vertices exist in this. All vertices have to be in the topological order. If they were connected, obviously all of them will be there somewhere. So this will be going to be obviously theta of V times this particular. This is nested, but if I go nested wise, I will not be able to do this. This individually or aggregate wise, this how many times it will execute. All edges will be covered corresponding to each adjacency list. All edges will be covered once and exactly once. So this step exactly works E times. So I can easily see that this will work E times. So overall, this complexity is again nothing but theta of V plus E. Plus E because this is E times, this is V times. So this all contributing towards this, the total being theta of first plus E. So total time complexity straightforward becomes theta of V plus E. And negative weights also get handled. In the book example is given, you can read that, but you can easily see that will be covered. Or otherwise, I'll take one example because in online, I can spend a few extra minutes. And I will take one example which is given in the book and I'll go through that. Let's say this was some vertex 5. Then I have vertex 3, which is my source vertex. So I am using the same example, just the vertex naming I am keeping 1, 2, 3. Then I have, let's say, vertex 4. Then I have, let's say, vertex 2. Then I have vertex 1. And then I have vertex 6. And the connections which are available are this 5, 2, 7. And then I have -1. Then I have -2. I also have a connection from vertex this to this with weight as 4. I have also connection this as weight 2. I also have a connection like this with weight 1. And I have a connection from source to this as, let's say, weight 6 and like that. Similarly, from 5 also I have a connection like 3. So this graph, sample graph I am using as in the book. Now I can easily see that initially vertex 5 all have the distance plus infinity. This has a distance 0. I'm putting a square for this, or I'll use a different pen also. Maybe initially I'll put in all these distances in this way. Later, these will be relaxed. So in topological order, from 5, I will start. So 5 can be ignored also, because effectively, even if I go via 5, the distance is going to be infinity plus weight of UV. So effectively, no relaxation will happen via this, guaranteedly. So till your source doesn't come, I can ignore also. The vertices may be ignored. Even if I don't ignore, I can probably just apply relax without resulting in anything. So initially, effectively, this vertex 5 will remain as it is with infinity. Nothing else will be done, whatever happens. Once we reach to 0. So after 5 covered, effectively, this 5 covered, and now I select vertex 3. This distance is 0. So this was step 1. In topological order, nothing change will happen. Step 2, this selected. Step 2 will mean corresponding to 3, this outgoing edges are going to relax certain weights or certain distances. Let's see that. So from 2, I have this going, I have this going. So via 2, because of this, 4's distance will be relaxed, and this will become 2. This is 0 plus 2. And via 3, this will also be considered, and vertex 2, this distance will be updated 0 plus 6, 6. There is no further outgoing from 3, no further relaxation possible. So now I claim after this, step 3 will come and I will reach to vertex 4. And obviously you can see vertex 4 has no further incoming connection. Nobody else can relax further 4. So this distance is final. So this is final. Then from 4, further relaxation will be attempted. Relaxation can be for this. For this, so this also can be relaxed, this also, these 3 edges can relax. So we will see one by one. 4 to 2 via 7. So this will mean a 2 plus 7. This is a 7. 2 plus 7 will become 9. This is already okay. So it is already okay, less than 9. This is less than 9, so not to be considered. This 6 remains, so not 6 considered. Via 4, if I consider edge 4, 1, 4, 1 will have 4. 2 reaching via vertex 4 was a 2. So if I consider this, this is a 2 plus 4. This distance is a 2 plus 4. For vertex 1, distance will become 2 plus 4. This again becomes a 6. 2 plus 4 becomes a 6. And now this 6 becomes a final. Similarly, 4, 6. Will further do some relaxation for 6. For 6 earlier it was infinity. Now it will be 2, this 2 plus this 2. So this will be 2 plus 2, that is 4. This relaxation happens all over. Step 3 final. Then we reach to step 4. Come to vertex 2. Vertex 2, again, I claim this distance is final because there is no further relaxation on vertex 2 possible. Then 2 is outgoing to be considered. This is 1 minus 1. So now you can see how minus 1 will make an impact. Minus 1 will mean this distance will be 6 minus 1 equal to 5. Better than this. So this old will be removed. And now it will become improved or relaxed distance as a 5 for vertex 1. Similarly, I have this one. So this one will also be considered. This to be considered vertex 2, 6, edge 2, 6. Edge 2, 6 will mean earlier 2 is a 6. So this side I am reaching via this vertex, which is, say, drawing like this. This is 1, and via this it will become 6 plus 1 equal to 7. 4 is already better. Okay. So this will not be considered. This will not be used. So I remove this and show that this will not be considered. After this, this becomes final. Step 5. So 1 is final. From 1, I have reached with distance of 5. This vertex exists. -2 will mean 5 minus 2. This is 5. This is -2. This is going to change because via 6, if via 1, if I come, this will be 5 minus 2, that is 3. Better than this. So 6 vertex can be reached via vertex 1, and this becomes via 1, 6. So I will say this distance will become 3, and via this also covered. So then it will be this answer final. So everything is finalized. So this way you can see that this ordering helped me in finalizing each vertex whose distance is guaranteedly correct now, 1 by 1. So this becomes DAG for negative weights. Bye-bye. Try to implement this also. So I will say again, implement for both. Implement your DAG shortest path for using adjacency list as well as adjacency matrix. Both you must try, and using both you will have enough confidence to do better programming. So do this and try to learn all this. So data structures we have discussed, and then accordingly you can implement. So I'll stop here and